The problem statement from GATE Physics 2020 reads as follows. Consider the circuit given in the figure. Let the forward voltage drop across each diode be 0 0.7 volts. The current I in milliamps through the resistor is. We are required to find this current I. The units are in milliamps. We are given three diodes, and it has been given that the voltage drop across each of them is 0 0.7 volts. This is a numerical answer type question, and we need to find our answer, and we'll fill in the blank here. In this figure you can see some physical diodes. These are available in the markets. You might have seen them in the labs. We'll be interested in seeing how to model these diodes. What is a model? See, a diode is an electronic device. It's not a straightforward device as a resistor. We call them active devices. So it has to be modeled if we want to use them in circuits, and we want to solve simple circuit using a simple KCL and KVL. We model them so that we can replace our devices. So what I want to do is I want to replace my diode with a combination of, let's say, voltage source, resistance, maybe some capacitance, I don't know, inductance and whatnot. So we'll ignore L and C for now. We'll just see that whether this simple humble diode, can it be expressed in terms of just say, let's say, voltage sources and some resistances, so that we can simply apply our KCL and KVL. This exercise is what we refer to as modeling, and this you will see across, not just for junction diodes. You must have seen this in BJTs, small signal equivalents, FETs, field emission transistors and whatnot. So a very simplistic model is shown here. This is an ideal diode. This is a diode. So it's operating as a switch. When you apply a forward bias, switch is closed and an infinite amount of current can flow. When it's reverse biased, so which is shown here, you can see the polarity has been reversed, the switch is open and no amount of current can flow, which is shown here using zero current, the horizontal line. Now what this means is that even for a very small voltage, let's say you apply 0.1 volts, you can get a huge amount of current and thus a huge amount of power. This is not realistic. However, this model, what I call as a semi-real or semi-ideal diode, what happens is that it's equivalent, it's taken forward from this. So this is, let's say, first generation, gen 1, and this is gen 2. So what is the modification that we have done? We have said that it will conduct, this diode will conduct only after a voltage of 0.7 volts. You can see a line rising here. This is what we sometimes we refer to as knee voltage. On the reverse side, this is the same as this. So if you apply a VD of negative, you can see the polarity has been reversed, no current will flow. So effectively what we have transformed this circuit to this or this, depending on the polarity. This is what I refer to as when I say we can model this somehow. So we have replaced this unknown black box using a simple switch and a voltage source. What I call a semi-real or semi-ideal is not the true picture. This will give you a true picture. So we have forward operating region, we have a drop voltage, and we have a leakage current, and then it breaks down at a certain voltage, which is called reverse breakdown voltage. But we'll stick to this model, the semi-real model, because the question itself says that a drop of 0.7 volts is there across the ideal diode. Now I have just reproduced the circuitry here. So let's assume the current I is flowing, which is we require to find the value of I. Now as we saw that we can model each of these diode when it's conducting. So you see that the current I will flow only when each of these three diodes is conducting, and we saw that we can, this is a diode, and we can simply, when it's forward biased, we can simply replace it with a battery of 0.7 volts, right? This is the equivalent circuit in forward direction. So let's do that. Let's convert this circuit into a simpler circuit, which we can then apply KCL, KVL and other equations. So this node is given 10.1 volts. This is 1 kilo ohms, and now we'll have three batteries back to back, right? and this end is grounded, and this will be 0.7, again 0.7, and the third one will also be 0.7, and a current I will flow here. So we'll try to find out the current. Now if we simply apply the the KVL in this loop, so you can, or in this leg of this of our electronic circuit, so I can write applying KVL in the circuit, I can simply say 10.1 minus IR, so the current is I and the value of resistance is 1K, minus will 0.7 minus 0.7 minus 0.7 equal to 0. So all of these have been replicated there, and finally this is ground, so is equal to 0. So I'll take I into 1K to the other side, so it will be I into 1K. This will be equal to 10.1 minus, so 3 times 0.7 is 2.1, so that's nothing but 8. So I will come out to be 8 over 1K, which is nothing but 8 milliamps. So very straightforward thing. So we just apply, we know that this diode in an ideal condition can be modeled with a voltage source of 0.7 volts, and we did that. And in the forward condition, note that in reverse condition, this is an open circuit, this is an open switch. So we did that, and we found out that the current is simply 8 milliamps. So we just applied KVL, and we find out that the current is nothing but 8 milliamps. So let's write this current here. Units is milliamps, so we'll write is 8, and that would be our answer. Thank you for listening.